Well, we're happy to have Peter Ozsvath today. He's going to talk to us about Heegaard-Floer homology and its applications. Next week we'll be back at the usual time, and Nikita Nekrasov will talk about TBA. Today we have Peter.
Okay. Okay, so I'm now going to talk about Heegaard-Floer homology or maybe I should, to put in a bigger framework, it's sort of invariance for low dimensional manifolds that are inspired, topological invariance for low dimensional manifolds that are inspired from symplectic geometry. And specifically, I'll talk about one of these, which is Heegaard-Floer homology. So I'd like to first talk a little bit about where it fits, where it came from, and then what we want from it, and where hopefully we're trying to go with it. And this might give some sense of we have a seminar. There are going to be lectures. I'm hoping that sort of to kind of give that some kind of outline. So great. So what is the origin of Heegaard-Floer homology? Where did it come from? So I should say that there were these familiar invariants for, or how should I say this? There was a sort of revolution in low-dimensional topology started by Donaldson, and the idea was the following. His idea was the following: that I'm going to sort of say it in some sort of. You start with a smooth four-dimensional manifold, and you equip it with a Riemannian metric, and consider an associated moduli space of solutions to some partial differential equation. These are in the case that Donaldson studied, the name of the partial differential equation was the anti-self dual Yang-Mills equations, ASDYME. Beautiful name there, ASDYM. So this is a particular partial differential equation that came from physics, nonlinear elliptic partial differential equation, and the idea is to consider the moduli space of solutions to this partial differential equations and do algebraic topology to that space. So the sort of on the crudest level, you might say if
the second order equation came from physics. Did also the first order equation?
I think it did. Yes.
Came from physics as well.
I think so.
Beloved Polakov, Schwarz, and Jupiter, 1975.
Great. Okay. So we consider we sort of on the crudest level we could just count how many solutions there are. If you're lucky, this is a compact space, zero-dimensional space, so it makes sense to just count how many points there are. By algebraic topology, I mean you have to carefully count points. So the simplest case is that you might look at the number of points modulo 2. And show that for a generic choice of metric, that count of points is independent of your choice of generic metric. And in that situation, this count gives you a topological invariant. In the case of the anti-self dual Yang-Mills equation, it gives the Donaldson invariance for a smooth four manifold. These are smooth. So one shows that they're independent of the choice of Riemannian metric. Therefore, they depend only on the sort of underlying topology of the manifold. They use calculus on the manifold, and therefore they depend on a smooth structure. And amazingly, they depend interestingly on the smooth structure. So they can identify manifolds that are homeomorphic by work of Friedman, but not diffeomorphic. So this is these were very powerful invariants. They were able to prove new things about four-dimensional topology. They were introduced sometime in the 80s.
As long as B2 plus not equal 1, right? Why there is...
Yeah, so there's a lot of technical points that I'd like to just sort of not address in this talk. Part of it doesn't work for all smooth manifolds. These have to be compact smooth manifolds. We have to make some hypotheses on the algebraic topology of the manifolds. Otherwise, the story breaks down. But I'd like to be a little bit vague about that. So these ideas were due to Donaldson from the 80s. And a new revolution happened in '94 when the physicists Seiberg and Witten introduced a new set of equations, a new set of nonlinear elliptic first-order partial differential equations with which one could play the same game, except that they were much more useful because, or not more, they were sort of more at hand, more user-friendly, because the moduli spaces one got were did not. So in the Donaldson case, one had to compactify moduli spaces. In the Seiberg-Witten case, the moduli spaces were compact for free. And one got a similar set of invariants called the Seiberg-Witten invariants. I say here 80s because that came before I wrote my PhD. And this came in some sort of like very magnificent moment right after. Magnificent, slightly traumatic moment when the whole subject got turned upside down. So Heegaard-Floer homology grew from my attempt with Zoltan Szabo to find a combinatorial way of describing these equations. And so our goal was to take a four-manifold, think about it, get some combinatorial object one could define, and that would be the four-manifold invariant. The idea being that somehow this whole process of boiling a topological invariant out of a space seems very unsatisfactory. You take a space, you put on a Riemannian metric, then you do PDEs. You ask the physicists to kindly give you a PDE. Then you study its solution space, and then you do algebraic topology, and poof, you get a topological invariant. That's not how topologists like topological invariants to happen. So we were trying to understand this, but maybe I should say one more piece of structure before I go on to our story, and that is this was already clear in the late 80s with work of Floer, and certainly inspired by ideas of Atiyah. And the idea was that that how can, and so of course ideas of Taubes as well, how can one can one study these invariants? So the idea was that if you're studying a topological invariant, there are things like Mayer-Vietoris sequences that you can apply, and that's how you can understand invariants. The picture that one wanted for these Donaldson invariants was the following. What happens to Donaldson invariants of a four-manifold when you cut it in two along a three-manifold? And the idea was that to a three-manifold, one should associate an invariant, which is now called the Floer homology of that three-manifold. And it should have the following properties that for a four-manifold with boundary y, there should be a relative invariant, which is an element of this Floer homology. So this is now a vector space one associates to a three-manifold, and to a four-manifold whose boundary is that three-manifold, one associates a vector, and that should be related to the closed invariant by a gluing formula or product formula, where the Donaldson invariant from the left side pairs with the Donaldson invariant from the right side to give you a number, which is the Donaldson invariant of the glued-up manifold. So this is only slightly. Yes, this vector space has an inner product.
But that's
Right.
not Donaldson invariant anymore because it's on the bound. It has a boundary.
That's right. So this is a relative Donaldson invariant. That's right.
It's a new one.
It's a new kind of invariant. So this is the sort of framework into which this picture is meant to fit. And this,
If you reverse the orientation, you get the dual space rather than this space.
Oh,
has
okay.
an inner product.
Oh. Oh, it's an oriented space.
that's right.
Y is oriented.
Y is oriented and X is oriented as the boundary of Y. And if it's got minus orientation, you can think of it as a cohomology class, and then you can pair homology with cohomology. Great. So again, there's some sort of drastic simplification because the Donaldson invariant isn't really just a number, and that one can enhance this in various ways. But this story, as I've said it here, was largely worked out in the case where Y is an integer homology sphere by Floer in his instanton Floer homology groups. Now, when Seiberg-Witten theory came along, so I should say so. So HF for the anti-self-Yang-Mills equations was introduced and studied by Floer. In the case of when Seiberg-Witten theory came along, it became clear that this should fit into the same kind of framework, and there was a sort of version of Seiberg-Witten Floer homology. And really, there's a beautiful book by Kronheimer and Rivka who worked out the general case of this. So their theory fit into this framework. Now, so the way it seems natural, if you want to try to build up an invariant using topological ideas, to first try to build the three-manifold invariant. And that's really kind of the starting point for Heegaard-Floer homology. No, I'll do it.
Build that wiggly arrow there. Y goes to H.
Yeah, this is what we're going to start with, and then we're going to continue with this, and then there will be a definition here. But probably during the course of today's lecture, I'll stop somewhere around here. Okay, so
Is there a full-blown story now of Y is arbitrary in either version?
yes, there's a full-blown story both in Heegaard-Floer homology and in Seiberg-Witten theory. So the Seiberg-Witten version is in their book. The Seiberg-Witten version is in their book, Monopoles and yeah, that's a full-blown version of the Seiberg-Witten version of the story. There's no full-blown version of the Donaldson version of the story, and the Heegaard-Floer homology was sort of built in a general case. It was not. It didn't help that it was. Well, I mean, it started out with the general construction. Okay, so let me give the idea of the construction of Heegaard-Floer homology with a little bit of the motivation. So,
In fact, isn't it fair to say that because of what you did, Heegaard-Floer homology, they understood what had to be done in Seiberg-Witten theory for the general theory?
you should ask them to give that.
Floer, I understand from the title, but Heegaard, how I mean.
So now we're going to introduce the work of Heegaard. So how is Heegaard-Floer homology constructed? So we would like to start with the three-manifold.
Before H stood for homology, now H is going to stand.
Yeah, I know. It's okay. So we start with a three-manifold, and we would like to give the three-manifold. So we'd like to construct a combinatorial theory. I should, of course, apologize. I'm not going to give you a combinatorial description, but I'll give you some sort of description that's almost combinatorial. So we're going to start with a three-manifold, and we would like a combinatorial description of a three-manifold. How does one describe a three-manifold combinatorially? Well, a wonderful way of doing it is called the Heegaard splitting. And Heegaard splitting starts from the simplest three-manifold with boundary you can think of, which is called the genus G handle body. It's the three-manifold with boundary that you get by taking a ball and then attaching a bunch of handles to it. This is the genus 3 handle body. It's a very simple. You could think of it as the regular neighborhood of a wedge of circles in R3. And it's a classical theorem in three-manifold topology that every closed-oriented three-manifold can be decomposed as a union of two handle bodies glued along their boundary. So this is a nice sort of very concrete way of describing a three-manifold. In fact, I'll make it even more concrete as follows. These are called Heegaard. That was a Heegaard splitting. A Heegaard diagram is the following. How do we describe a handle body with boundary sigma? Well, you can do that by taking G simple closed curves, which are homologically linearly independent, and each of them bounds disks inside of the handle body. Not in sigma, but in the handle body. They're homotopically non-trivial, but inside of the handle body, they bound disks. So that is to say, a handle body with boundary sigma is specified by, if sigma is a genus G surface, we give a G tuple of circles alpha 1 up to alpha G. That specifies U0. If you want to specify U1, then you take another such G tuple of circles, beta 1 up to beta G. And I would like, in addition to this, I would like one other piece of data. So here's an example of a not very interesting Heegaard diagram. I would like to, so these are, let's say, the red circles. They specify the alpha circles. And the alpha handle body, maybe I could call this U alpha, and I could call this U beta. The blue circles specify the beta handle body. And I'm going to pick one other piece of data, which is a reference point Z. Now, in this particular picture, in actual fact, the betas are going to, from the point of view, so okay, I should say it this way. If I take a genus G surface, and I take G different homologically linearly independent simple disjoint circles, they always, up to homeomorphism, look like a standard picture. But if I take two different G tuples of circles, then they won't simultaneously look simple. I draw alpha circles, then the beta circles are going to look kind of crazy in general. They didn't in this picture.
The intersection pattern is kind of invariant, right?
That's yeah. So I draw my alpha circles in some standard position, then my beta circles are going to look kind of wild with respect to the alpha circles. And I can have a different homeomorphism, which will straighten out the beta circles to make them look standard. Then that homeomorphism will take my alpha circles to look kind of wild. I can give you some actual picture. Should I give an actual picture?
So it's not connected to A and B cycle, or it is connected to it.
Is it A and B cycle?
Cycles on the surface.
They are not necessary. If you mean by A and B cycles, if you mean the standard set of circles that, then no, they're not. Or rather, the alpha circles would be the valid A cycles, and the beta circles are another set of valid A cycles. But they're not. There's no relationship between the two. They might look quite complicated one with respect to the other, and that's what accounts for all of three-manifold topology. Somehow, that's the difficulty of three-manifold topology.
Beta loops still bound disks?
The beta loops bound disks on the other handle body. So maybe I'll get here's a real life example, a real life but very simple example, which is misleading in some sense. So here's a genus 2 Heegaard diagram. This specifies the three-sphere. You see that these red circles bound disks inside, and the blue circles bound disks on the outside. But that would be one example. But here's another example that you can look at. This is genus 1 case. I can draw one curve, and I can draw any other homologically interesting curve. That's the Heegaard diagram for a lens space. So you can these are two very simple examples of Heegaard diagrams. Okay. All right. So this is our topological input, which is this Heegaard diagram for the three manifold. And You get both the p and the q. That's right. So now, I would like to. Okay, so this is our combinatorial representative of 3 manifold, and now we'd like to do some symplectic geometry. So we'd like a space on which to do symplectic geometry, and in again, I should say that in gauge theory, the natural symplectic manifolds that come up are representation varieties of the fundamental group of the surface. That's an algebraic variety, and one can sort of start to study those representation varieties. I'd like to actually consider a much simpler variety, which is the symmetric product. So I'm going to start with the surface of genus G, and I'd like to consider the G-fold symmetric product of sigma. This is the space of unordered G tuples of points on sigma. And you can think of it as the G-fold Cartesian product of sigma modulo the action by a symmetric group on G letters. So that is to say, these are unordered G tuples of points, except some points can have multiplicity. So for instance, in the case G equals 2, I've got just 2 points on this genus 2 surface, which are allowed to collide. Okay? And
when they collide, you put a 2 there.
I put a 2 there, that's right. And so it's one of the kind of great miracles of nature that this is a smooth manifold. And the name of that miracle is the fundamental theorem of algebra. So here's a little fun fact. The n-fold symmetric product of C is C to the n, because a monic polynomial is determined by its n roots or by its n ordered coefficients. So this is the local miracle, and sort of globally this can be made into the following statement, that if sigma is a complex surface, you look at its G-fold symmetric product, you get a smooth, I said complex surface, complex algebraic curve, then you get an algebraic variety. Okay, so
important that G is there and G is there is the same. If I would put symmetric.
no, I'm sorry, it's not yet important.
N is there.
I could do n. I have to do d because n is impossible. But yeah. So but we're very soon going to look at the case of G. Great. So so now this is going to be our ambient manifold sim G sigma, in which we'd like to do kind of some analog of complex analysis. And sitting inside of that manifold is a natural pair of half-dimensional subspaces. So what is that? What are those subspaces? Well, they're these tori. We had alpha 1 up to alpha g. We can look at their Cartesian product. So in other words, in this picture right here, I'm looking at the second symmetric product of sigma. Well, I could look at the product of these two tori, which is, if I'm doing, let's say, alpha tori. So I've got this red curve and this red curve. I can look at the locus of points where one point lives on this curve and the other point lives on that curve, and that's a nice smoothly embedded torus. So I've got the alpha torus and the beta torus, both of which sit inside of sim G sigma. And I should say there's one other piece of data that I wanted, which was a base point z that was disjoint from all my alpha and beta circles. And now there's a wonderful theory that one can plug into, which is the theory of Lagrangian Floer homology. It was actually defined by the same Floer, but it's a different Floer homology. And he had an invariant for Lagrangian submanifolds sitting inside of symplectic manifolds. Or rather, it's an invariant for a pair of Lagrangian submanifolds sitting inside of. Yeah, sorry. Okay, so symplectic. So I should start symplectic manifold. It was a symplectic manifold. A symplectic manifold is a 2n-dimensional manifold equipped with a 2 form, which is closed and which is completely non-degenerate, meaning this n-fold wedge product with itself vanishes nowhere. So it gives a volume form, and I could write that by saying that this is positive everywhere. Now this is what a symplectic manifold is, and this is sort of a natural framework in which to work. Maybe when you first see this, you think, oh, I know what an algebraic variety is. I know what a smooth manifold is. Why would one have to sort of do all this? But after a while, you just start to realize this is actually kind of the right framework for many points of view. As I'm sure we'll hear from the talks on the symplectic geometers. That's one of the many points, that's right. But also from the point of view of topology and geometry. Great. So this is what a symplectic manifold is. There's a natural class of submanifolds that one can consider, which are n-dimensional submanifolds of a symplectic manifold, which satisfy the property that omega restricted to L is identically 0. So n is the maximal dimension in which you could possibly find such a thing. And these kind of objects are in some, so these objects have a certain kind of rigidity and a certain kind of flexibility. So they're right at the correct place to do symplectic topology. The curves on a surface, maybe, yeah, they would be examples. That's probably, those are probably more flexible than what that might be misguidingly simple looking somehow, but that's certainly a picture. Now, so great. So Floer introduced to a certain extent an invariant for pairs of Lagrangians in a manifold, which is a chain complex generated by intersection points between the two Lagrangians. And I should be precise here, which is that Floer defined this only under very restrictive hypotheses. There's been since then a great deal of additional work done, and there's an extensive literature on this, and Fukaya is one of the world's experts on this subject. So, but at any rate, let me just say what I know. So we have a chain complex which is generated by the intersection points of these two Lagrangians, and its differential counts holomorphic disks in the following sense. A symplectic manifold can be endowed with what's called a compatible almost complex structure, J. So there's a complex structure which is supposed to be an involution. Sorry, J. It's an endomorphism of the tangent bundle of X, which whose square is -1. So this is somehow multiplication by I on the tangent space, and it's supposed to be compatible with omega in the sense that omega blank J blank should give a Riemannian metric on the the symplectic manifold, and sometimes it's convenient to also demand that J respect this inner product. So we will just fix once and for all such a choice of J. And with that said, then there's a notion of holomorphic disk in X. This was introduced really by the seminal paper of Gromov as a tool for studying symplectic manifolds. But anyway, so we now think of our target space X as having this complex structure on it. Then it's natural to consider holomorphic curves in it. In fact, we're going to consider holomorphic strips. That is to say, we're going to do the following thing. So we've got this space with these two half-dimensional manifolds, L0 and L1, and we would like to count we want to define our differential, and to define our differential, we're going to look at holomorphic maps of the standard. I'll write it this way. Of the standard disk into our space, which send the left half arc to L0, the right half arc to L1, and they're supposed to be holomorphic, which means that they satisfy a Cauchy-Riemann equation, which you write down with the use of this J. And they're supposed to send I to the point X and minus I to the point y. So we can assemble the space of such maps into a moduli space, mxy, and make some observations about it. The first observation is that that satisfies a natural translation action on it by, if you think of this as really an infinite strip, then the translation is just your standard translation, vertical translation. So one can divide out by that action, and then the differential of a generator can be written as a sum over all other generators of a sum. Well, how should I write this? We just count how many points there are in this moduli space connecting x to y divided by r times y. That's loosely speaking the idea. There are many things to be said to make this more precise. First observation is that this space is typically some singular manifold, if you like. But I want to only count. I want to assume that I'm going to look at the one-dimensional moduli spaces of flows and divide those out by r to get my finite counts in the definition of the differential. This definition is motivated by looking at Morse theory in a way which I don't want to go into any further, but it satisfies this property that d squared equals 0. So it is a differential. That's a fact about.
A very important and more precise version of that remark is Floer was inspired by Witten's description of Morse theory.
That's right.
To come up with this idea.
That's right. Okay, so Floer was in fact reading a Witten's paper on supersymmetry in Morse theory. Right, so this satisfies this equation d squared equals 0, which you can think of as a manifestation of a compactness theorem about holomorphic curves. This is Gromov's compactness theorem of holomorphic curves. Great. So this is a machine into which one can plug if one has a symplectic manifold equipped with a pair of Lagrangians satisfying suitable topological restrictions, which I didn't bother to say, but they're satisfied in our case. So what we'd like to do is, I've already told you what our ambient space is and what our two symplectic manifolds are. So now we can just essentially plug into this machine to construct an invariant of 3 manifolds. Well, okay. To construct a chain complex associated to the following data. I take a 3 manifold. I take a Heegaard diagram for it. I mumbled something about choices of almost complex structure there. That's roughly speaking equivalent to choosing a complex structure on sigma. This is a slight lie, but not so terrible. So I choose a complex structure on sigma, and from that, I associate my G-fold symmetric product equipped with its pair of tori. And from that, we construct a chain complex.
So that symplectic space, just like Floer,
Yeah?
is what? Symmetric product of?
The G-fold symmetric product of the surface of genus G. And now G is important because, so I've got this, in this picture, the third symmetric product. I have this torus consisting of triples of points that's half-dimensional if we're looking at the G-fold symmetric product. So now the genus G is important. And kind of the main sort of, the first theorem in this subject is that the Floer homology, the homology of this chain complex, is a topological invariant. Of the 3 manifold. This is theorem I proved with Zoltan. So I should say maybe a few words about making this a little more precise. We don't actually count all holomorphic disks. And there are several versions of what you do. But the simplest version, you only look at holomorphic disks that don't cross Z in the following sense. This point Z gives rise to a codimension 1 subvariety of sim G sigma, which is somehow Z times sim G minus 1 of sigma. So less formally, it's the set of those G tuples of points where one of the points is just Z. That's a complex codimensional 1 subvariety. And we can look at holomorphic disks that miss that complex codimensional 1 subvariety, and one gets this invariant HF hat of Y. If you want to be a little if you want to be a little more careful, there are other versions which are where you count how many times your disk crosses that point Z, and record that in the exponent of a formal variable. That's a theory, HF minus of Y, which is a module over this polynomial algebra in a formal variable. So yes.
It's not obvious that this
is connected to the original, that other definition which had vector space associated to 4 manifold having by.
Oh, hang on. So this is the vector space that we associate to a 3 manifold. This is now, by definition, the vector space we associate with it.
I have 4 manifold, which is a boundary of 3 manifold.
That's right.
That vector in that vector
That's right.
knows about the interior.
That's right. So I haven't yet defined what the vector is. I've only defined now what the vector space is.
So now vector will be connected to the form.
That's right. And it won't be in today's lecture, unfortunately, because I won't have enough time. But I can talk to you about that later if you like. This is the sort of, okay. So it also shouldn't be so clear that there's a topological invariant. As you see, there are analytical choices that go into the definition, like the choice of a complex structure on sigma, that are hard to prove invariance of, but they're standard. They're sort of standard in Floer theory. What's not standard is that this actually, the independence of the Heegaard diagram. And sort of that's a long struggle. So this is a paper of ours from 2000. Okay. Pardon? Yeah, there are many different splittings of the same 3 manifold. You have to show this independent of that choice. That's right. That's right. Okay, so.
Do you get moves on the chain complex corresponding
Yes.
to the moves?
Yes, that's right.
Representation.
Yes, there are. There are sort of, and you check those are all isomorphisms, and that's how it goes. Okay, so anyway, I gave some sense of the definition of Heegaard-Floer homology. I hope that was somewhat clear. Maybe I could make this a little bit concrete in an example, but I also want to say some general remarks about the subject. But let me, in order to not just be spewing generalities, let me try to turn this definition to something concrete. Yes.
How much this story can be repeated for complex 3 manifolds? Like Calabias looks like that. Lots of things can be.
That's quite possible. I have no idea. I haven't thought about that at all. That's certainly a question worth investigating. So let me attempt to turn these holomorphic disks in the G-fold symmetric product into something friendly that we all can kind of relate to on some level. So we have a picture, some Heegaard diagrams. I've got my surface, and I've got this collection of G-tuples I've got these collections of alpha and beta circles. What is a generator in this complex? It's a G-tuple of intersection points where one point lives on each alpha circle and one point lives on each beta circle. And that's what a generator of this story is. So the generators you see are completely combinatorial. You draw the picture, you can just read off what the generators are. What is a holomorphic disk in the G-fold?
Can we extend one of those blue lines and let me see how many points there
Should I give you you want a real picture? Is that?
Just a little bit.
Okay, I can't do a little bit. I have to do everything somehow. It doesn't make sense. Then I'll do everything. Why don't I do that? So let me give you an example of a real Heegaard diagram. It has to be red. So let's see. Okay, that's very sad for the following reason. I drew it with only 2 colors. So let me turn one of these into, let me turn one of the circles white. So I'll turn this circle white. Okay, so here's a circle alpha 1. Here's a circle alpha 2. Now, how's this a circle? This is a genus 2 surface. I have a handle over here and I have a handle over here. So this alpha circle closes up inside of that circle. This alpha circle closes up inside of that circle as well. And now I have 2 beta circles. Here's a beta circle. It's this sort of, well, you can see it. It's that white kind of worm that goes around. And there's also a blue circle that does even more wiggling. It's spiraling going.
Copy of this picture, you're just forming the double? One in front of the
No.
back of the blackboard.
No, then that would be a different picture. No, I just imagine that there's a handle here, and this alpha red arc goes over to here, and that blue beta arc goes over there, and then I do another one of these. So it's not 2 copies of this picture. Hey, so let me just. I have.
What does that circle mean?
This is a 2. Oh, so A is identified with A. This is a circle that's identified orientation reversing with this circle. Or in other words, I'm just going to drill out this circle and drill out that circle. I'm going to attach an annulus, and I'm going to run this. So I do surgery on S2. I cut out.
Start with the blackboard cut out 4 discs.
Start with the blackboard, cut out 4 discs. Then I attach a handle to this pair of discs and another handle to this pair of discs. And then I run this alpha arc through that handle once, just like this.
The handle has boundary on the 2 discs?
Yeah. And it's just got these 2 parallel, an alpha and a beta just running along there. So nothing exciting is, I'm not hiding anything. Everything.
It's coming out of the board. And
Yeah, that's right.
Okay, fine.
That's right. I've drawn everything exciting. I haven't hidden anything. Okay, great. So here's a picture. What's an example of a generator? Well, I could take this point. That takes up alpha 1 and also takes up the white beta circle, and then I have to match that with an intersection point of this red circle with the blue circle. As you see, well, you can't tell because I haven't made this picture clear enough. I'm going to move this. Sorry, just a second. I'm going to make this clearer. Sorry, there are 3 choices of this white circle. Once I've made one of those 3 choices, I have how many choices for the blue circle? In this picture, I have 4 choices for the blue point. So
You use the first choice again.
I choose this guy. Let's call him x1. Then I can pair x1 with y1, y2, y3, or y4, and I get a valid generator. Or I could choose x2, or I could choose x3. So any of xi, yj.
Don't you need 2 points?
I do need 2 points.
Why
So
do you have all these subscripts?
because I have 3 choices for the first point.
Yeah.
I want.
3 choices for the first.
I have 3 choices. 3 of these choices for the first point, and I have then 4 choices for the second point. Or I could have chosen not type X. I could have chosen P1 or P2, and then I can match that with Q1, Q2, or Q3. So you see that there are 6 choices for that. So we've got sort of
18.
18,
30.
something choices of generators. And now, okay, great. So our generators are these nice concrete creatures. What's a holomorphic disk? So a holomorphic disk is the following picture. We're looking at sim G sigma. You take the standard disk and you color one of the boundaries red and the other one blue. And we want a G-to-1 branched cover of that disk. And that gives us a surface with boundary. And the boundary has this coloring with these alpha arcs and these beta arcs. sorry, not, it's coloring. I color something blue if it projects down to this blue arc, and red if it projects down to this red arc. There can be several pieces. There can be genus. They can be disconnected. It can be.
The bands could have several blues.
That's right. There might be two blue arcs and two red arcs on the same boundary component. That's right. And I have a holomorphic map of that into sigma, which sends the red arcs to the alpha circles and the blue arcs to the beta circles. That is what a holomorphic disk is. Holomorphicity, just means that all the arrows are also supposed to be holomorphic. So I'm supposed to choose a complex structure here for which this is a branch cover, and this map is a holomorphic map. So these are.
You just have the topological picture. You chose a complex structure there and a complex structure there. They wouldn't meet when you pull them back.
That's right.
So you have to have meeting complex structures.
Exactly. That's right. That's right.
That's why it's not just topological.
That's right. That's right. It's very close, but it's not quite there.
You do have some freedom down in the bottom because you can move where the branch points are.
Yeah. Right. And you have freedom over there.
Yeah, I can move that too. As you can also move the match points here. Okay, great. So anyway, this is what a holomorphic disk is. Maybe I'll give here's a simple example. Suppose I have two different alpha circles. Suppose we're in the second symmetric product, and we have two different alpha circles and two different beta circles. And suppose that I can find a square in my diagram that looks like this. So this is now a generator. Oh, I should, sorry. This is P. This pair of points P is a generator, and this pair of points Q is another generator. Yeah, I have many others, but I'm going to, in this picture locally, I have two, P and Q. Then this rectangle represents a holomorphic disk in the second symmetric product. Why? Because for any choice of complex structure on sigma, I have some quadrilateral over here. A quadrilateral is always conformally equivalent to a rectangle with some modulus. And that's right. And there's a 2-to-1 map of the rectangle. There's this 180-degree rotation gives you a 2-to-1 map downstairs. So for any choice of complex structure, this always gives you a non-trivial differential. So these are examples. Okay. So great. So now I've given some sense of what a holomorphic disk actually is.
Fix the complex structure on sigma.
Yeah, and in this story, you want to once and for all fix a complex structure on sigma and then use that. Then you prove that the invariant is
real modulus there.
Pardon?
On that rectangle.
There is a modulus. There's a real modulus on here, but the answer didn't depend on that. In a more complicated picture, if you pick for me kind of two generators that are connected, the answer will depend on some kind of moduli. So it's not going to be, this is, again, sort of a little misleadingly simple. Okay. Great. So now I'd like to completely change my...
Let me see if I understood that remark. In this picture, you had a topological picture. You said it's automatically going to give a holomorphic disk. Was your last comment that more generally you can't tell from the purely topological combinatorial patterns what are going to be holomorphic disks and what aren't?
That's what I said, yes. Probably less coherently, but that's what I was saying. Okay. Great. So let me now kind of.
If you're lucky in this case, with 4, you get it. You can always find it.
Let me kind of give some kind of idea of where this story fits in with the rest of its immediately surrounding pieces of mathematics. So here we have a theory, Heegaard-Floer homology. I'm sorry, I'm going to present now a Heegaard-Floer homological centric view of the world, but that's unfortunately the world I occupy. So Heegaard-Floer homology was inspired by ideas from gauge theory. And in fact, from its construction, we conjectured that our Floer homology invariant is isomorphic to Seiberg-Witten Floer homology. So that gives an extremely close connection between these two theories. They were conjectured to be isomorphic. In fact, there are now two groups of people who are, there's Kutluhan, Lee and Taubes, and Colin, Gigini, and Honda, who are verifying this conjecture to various levels. So we're going to presumably have talks by at least some of these people to tell us exactly the state of the art. My understanding is that on the level of three-manifold invariance, the isomorphism is verified, and it goes via another theory, which is embedded contact homology. So again, this is very current, very exciting development in the subject. These are the two groups. Yeah. Great. And so that there's that level of interaction. There's also interaction with contact. Well, so what other subjects does this interact with? One is categorification. And
So if you use the Heegaard-Floer homology and construct the color product of the vectors they will construct using this decomposition, then you will get Seiberg-Witten line. Not Donaldson line, but Seiberg-Witten line.
that's a statement. I haven't made that statement. What I still said, I tried to say something a little that comes earlier than that, which is that the Heegaard-Floer homology constructs a vector space. And gauge theory, Seiberg-Witten theory also gives a vector space. And I think the state of the art now is that these two vector spaces are isomorphic. I don't know what the status is of the vectors themselves.
Define the other vectors.
Pardon?
It defines the other vectors.
I did not define this vector space. I didn't define. It's in Kronheimer and Rivka's book. Great. So I want to say my title has the word applications in it. So I should say something about applications as well. So in fact, let me say that before I move on to categorification. So Heegaard-Floer homology. So okay, this is four-manifold topology. Should be writing it over here. So gauge theory was a tool for studying four-manifold topology. And so through that connection, Heegaard-Floer homology should be connected to it. Now, in fact, there were also questions in three-manifold topology and questions in knot theory, specifically, with which Heegaard-Floer homology kind of naturally interacts. In fact, Heegaard-Floer homology does its best for answering questions in three-manifold topology and knot theory, questions that are actually secretly four-manifold questions in disguise. So I could go into this in a little bit more detail, but probably not in my remaining amount of time. But I should just say there's this there are questions about what's called Dane surgery, and Dane surgery is well, it's the following operation. It might not seem so natural to the outsider, but it's the following operation on a three-manifold. Let's say S3. We take S3, we take a knot in it. Then we can drill out a little neighborhood of that knot. And we can glue back in a solid torus via some other diffeomorphism of the torus to itself to get a new three-manifold. And one can ask questions about starting from a so given a knot, and it turns out that this parameterization is classified by some rational number. This is a knot sitting in S3. Associated to that, we have a new three-manifold. One can ask questions like, to what extent does this description remember the knot? Or how many different ways what can you say about three-manifolds that can be expressed in this term? So stepping back a moment. If we allowed not knots but links, so that we allowed for many components, then we could get to any three-manifold that way. But one can ask, what can you say about three manifolds that you get in one step like this? And to what extent that three-manifold remembers the knot. These are called Dane surgery questions, and Heegaard-Floer homology is particularly good at answering those questions. I'll come back to this if there's interest.
Do you use the conclusions of the geometrization conjecture?
No, no. For these, we haven't used geometrization.
Describe.
Yeah, actually, you know, geometrization was also known for knot complements. But actually, we don't. That hasn't played a great role in this relationship. It should probably play more. So maybe a good question is, to what extent does Heegaard-Floer homology interact with geometric structures, hyperbolic geometry, and that's still quite poorly understood. Let me say another point of interaction which is understood better, and that is categorification. So categorification is an area where so these were invariants for knots. The sort of most successful current theories are invariants for knots that are constructed using ideas from representation theory. And there is quite a bit of interaction between Heegaard-Floer homology and categorification. There presumably should be more, but
Categorization related to those non-invariants defined by representation theory.
yeah, let me be more,
Okay.
just more. Okay, but let me still be more explicit. Let me give an example. There's a if you have a three-manifold invariant, then you automatically have an invariant for links, which is gotten as follows. Given the link, one can construct the branch double cover of that link, which is a three-manifold with a 2-to-1 map down to the three-sphere, which is branched over the link itself. So the preimage of a point downstairs in that link is just one point upstairs. Everything else has two preimages. And you can apply your invariant to it. In this case, we're going to do HF hat. So there's a remarkable invariant that was defined by Chovanov, which is called the SL2 invariant, or Chovanov homology. It's an invariant for links in S3. And for the unlink, it agrees with Heegaard-Floer homology, the branch double cover, and it satisfies the same kind of. Chovanov constructed it in such a way that its Euler characteristic is the Jones polynomial. And as a result, it satisfies a certain exact triangle, which is also satisfied by Heegaard-Floer homology, the branch double cover. And so this is more than a coincidence. In fact, there's a theorem which Zoltan and I proved in 2003, which states that there's a spectral sequence which starts at Chovanov's, at some reduced version of Chovanov's categorification of the Jones polynomial, and converges to HF hat of the branch double cover now. So this is an example of a relationship between Heegaard-Floer homology and categorification.
Build the differentials.
Yeah, you have to build. Well, there's somehow
Differentials are not part of.
in that spectral sequence. That's right. They're not part of the Chovanov theory. That's right. They're somehow hidden in Heegaard-Floer homology.
Is it true actually that from this Heegaard-Floer homology you can describe some object like R matrix, an algebraic object like R matrix? So it's too much. Only product of it you can identify with invariant.
I'm not competent to answer that question. I don't actually know what an R matrix is, but maybe if you tell me, I'll after.
Something which enters in Jones polynomial as kind of element.
Okay,
In Chovanov's case, I think one can say.
Okay, I can't answer the question in real time, but I can. We could talk later. So I wanted to say one other link, and then I'll stop. And that is, there's a close connection between Heegaard-Floer homology and contact geometry. So, not surprisingly, well, you might say, well, its construction has to do with symplectic geometry. But this is a slightly different connection. So there's for a three-manifold with a contact structure, there's an invariant in Heegaard-Floer homology, which can be used to study contact structures on three manifolds. And there's a sort of corresponding story for the cases of knots in three manifolds. So there's a close connection between contact geometry and Heegaard-Floer homology. And I hope during the course of this program we will be exploring all of these various connections. So maybe I should just stop here. Yes?
Can you say one 10-word sentence about how you interact with contact structure with previous discussion?
Okay, so that's actually a great question, and I can't do it in 10.
Well,
It'll be like some number of sentences.
10 to 10.
But the great link. So I was, you know, when we were first defining this, I was sort of depressed that this was the one thing of just, it's like gauge theory. We'll never be able to do it without gauge theory. But just around the same time, Giraud proved a wonderful theorem in which he defined contact structures, gave contact structures almost geometric definition. So he, yeah. So he showed that if
Didn't hear his name.
Giraud,
Oh, okay.
if L is so there's this notion of open book decompositions of a three manifold. An open book decomposition of a three manifold is essentially it's almost a fiber bundle. So you take a fiber bundle and you take a surface with boundary, and we have some automorphism of that surface with boundary, which fixes the boundary. Then there's a natural that gives you a natural three manifold with torus boundary. And if you sort of surge out the boundary in an appropriate way, not in the fibered way, but in the opposite way, one obtains what's called an open book decomposition. And Giraud proved that there's a one-to-one it was known classically, work of Thurston and Winkelkemper, that an open book decomposition gives rise to a contact structure. But Giraud proved an amazing correspondence, a one-to-one correspondence, where one has to look at open books modulo a certain equivalence relation. As I've said, it's sort of tautological, but Giraud actually spelled out what it was. So this you could think of essentially as a knot in a three manifold. And from that knot in the three manifold, we could construct an element in the Floer homology. And then we showed that element was independent of the actual open book in under Giraud's equivalence relation. And that's how it gives this invariant. So that's sort of one of the links with contact geometry. There's more to be said.
So the open book goes on the two-headed arrow there.
That's right.
The open book decomposition.
That's right. There's a little more that can be said about this, but maybe I won't.
Was some infinity algebra, I think, constructed by Chicano for contact manifolds. Is it of any relation to this construction? Or?
That's an interesting question.
For Legendre knots.
Legendre knots.
Oh, I see. Yeah. That relationship is not. What's the relationship between this and Chekanov's invariance for Legendrian knots? I don't know of any direct relationship between them. Yeah. I mean, so one can construct invariants for Legendrian knots using Heegaard-Floer homology. They seem to contain different information than Chekanov's invariants, though, you know, there might be some relationship someone finds at some point. Maybe another piece that I haven't said is that one place where this subject is very active is sort of computational tools. The description I gave is still holomorphic, but there are many computational tools now for Heegaard-Floer homology. But I'll be happy to discuss that in private.
Are you able to define the element for a four-manifold with boundary?
Yes, one can define the element for a four-manifold with boundary. It doesn't go much past the. So what you need are holomorphic triangles. Another construction from Lagrangian Floer homology. The definition of that invariant element is not so difficult.
But it's not known that it's the same as the Seiberg-Witten.
I don't think anyone has claimed that yet.
It's not known because it's not really kind of done. So I think there is a program kind of working in place, but not finished.
Yeah, that's right.
And then presumably you would get the Seiberg-Witten invariance, get the same gluing formula.
Yes, that's right. That's right.
The element has not been described, but when you glue, you told me that you will get.
No. I'm sorry. The element.
That was a statement about Seiberg-Witten invariant as a scalar product.
That's how much I've heard claimed in lectures.
Oh.
I think it's natural to conjecture. So one knows how to construct the two elements and the two sides, but I don't think anyone has claimed that that's been identified. I don't know how much beyond what's known that would be.
So what's the analog was it when the scalar product is a Donaldson line? Because it started sounded like that you will end up with a Donaldson line, but you ended up with
So there in fact is a conjecture called the Heegaard-Floer conjecture, which states that that the Donaldson invariant is a Lagrangian Floer homology of a pair of Lagrangians sitting inside of the character variety of the splitting surface. So if you have a surface, sorry, I'll just say it again. So if you have a Heegaard splitting of a three manifold, you can look at the character variety of that three manifold, and you get some kind of singular algebraic variety. And that comes equipped with two natural Lagrangian submanifolds, which are singular. Actually, they're not manifolds, but two natural Lagrangians. And one of the inspirations for us was that there was a conjecture by this Heegaard-Floer conjecture that stated that instanton Floer homology should be the Lagrangian Floer homology of that pair of Lagrangians. I've heard that statement. I haven't understood a rigorous statement of that, because these are singular spaces in which we're working. I don't know the precise status of that conjecture, but that should give you back the Donaldson invariance. But
there is a kind of formula that people kind of probably know is how to construct out of Seiberg-Witten Donaldson.
That's true too.
You have the vector constructed. You can construct a vector in some vector space associated to four manifolds with a boundary,
Yes.
such that the norm of that vector is a Seiberg-Witten invariant.
That's right.
Now, in the other case,
Yeah. So
the question of how one vector relates to other vector.
actually, the question is, how does the vector space of instanton Floer homology relate to the vector space of Seiberg-Witten theory? And I don't think there was a program to understand that which was abandoned. So to my understanding, so I don't think that's understood at all. So I think that obviously is something that should be understood, and we should be embarrassed as a community that it hasn't been understood. But it's not. So we don't understand the relationship between the instanton and Seiberg-Witten Floer homologies
It's not
at all.
conjecture. I mean, we know what the answer is for four manifolds. Maybe we haven't quite proved it. There's not even a conjecture, as far as I know, how these vector spaces are related.
That's right.
There was this paper by Michael Shadows with some kind of this go up and down.
Yes, I think we should continue this conversation maybe later.
Well, just one piece, you made a comment, you don't know how to precisely formulate the Heegaard-Floer conjecture.
That's right.
I believe Max Lippiansky feels he can prove it, so he must be able to formulate it.
Well, we should get him to explain it to us.
Analysis.
Lipyansky, Max Lipyansky.
Max Lippiansky.
Yeah, well, he's at Columbia, I think. Well, so we should get him to come over.
Columbia.
Yeah, we should get him to come give a talk there.
No, he wanted to come here for a year and write up the proof.
Uh-huh.
That's why I mentioned it in public like this.
Oh, we should give him. Okay. All right.
To be continued.
Yes.